So first of all, I'd like to welcome everybody, and most particularly to the students who are taking this course. As I go forward, I'm going to try and explain what I'm trying to do and how I'm trying to do it. So hopefully there'll be a little bit of a story here, a little bit of a thread that you'll be able to follow. So the first slide here is essentially talking a little bit about myself. It was part of the advertisement, I think, that came from ITMO, but it's also got my contact details. If possible, I'm going to try and circulate all this lecture material to the students. So again, if you don't see something or you miss something, don't worry too much about it. The other thing I'm going to try very hard to do is I'm going to try and very, very hard to speak slowly and carefully, because I know there's a language barrier. And believe you me, your Russian is a lot better than my Russian. And I'd hope that my English wouldn't be too bad. But please, if you don't understand something, there'll be a video hopefully that you'll have access to after this. And don't be afraid to ask questions. So my email address is given there and some web information. And I really, really do like the idea of students being involved in asking questions. So a little bit of a potted CV there. And that's me looking particularly clean and organized. So I don't usually look that clean and organized, despite the best efforts of my wife. And this is, each one of the little pictures here is a little story about research we've done. It certainly isn't, and this is really with my group. It's not just me alone. So it's a little bit of information. And again, maybe at the beginning of every talk or in between the talks, we'll try and break it down into pieces, digestible pieces. I might go back and tell you a little bit about some particular piece of work we've done to do with holography, or maybe to do with something different from holography. This here, if you can see the cursor that are moving on the screen here, this here was an event during the International Year of Light when we lit up one of the largest monuments in Ireland. So I've got video on that as well. It's quite interesting. And all the other things have to do with different research, with state funding and EU funding, or with companies, a whole range of companies down here. And I've started several companies, and I've done some books, and I've worked a lot in the area of optical signal processing, which is, I separate out slightly from what I've done on holography. So as I said, we'll come back and we'll talk about some of these things later. And if you've got questions, please ask them. And the other thing is that I'm speaking to you here from Ireland, which is over here, and most of you will know generally where Ireland is, but it's probably as generally as I know that that's where St. Petersburg is. And this here is the island itself. And I'm based here. I'm based in Dublin, the capital city, in University College Dublin. But I originally come from over here in the western part, over here in a county which is called Mayo. So in Ireland, we have the Republic, we have provinces, which are subsections, and then we've got counties. So every country has got its own little rules and regulations. Ireland is very, very small. As I told the people who helped organize this, when they asked me for my passport information, they were, I think, a little bit surprised to find out that just there was one office in the whole country that gave passports. Now, this is the list of students I have who are attending this course. And if you think you're registered and your name isn't here, then you're not registered. So please make sure you're registered if you're supposed to be attending the course. And on the other hand, if one of these people is your friend and they're not here, or they didn't know the lecture was on, you might just remind them of the timetable for the lectures. So it would be very good if we could get everybody here on time. As I said, this will be videoed, so if people are very busy, they'll be able to go back and look at what happened. But again, and if you can't get to a lecture, it'd be nice to know. Yeah, so make sure somebody knows you're not coming. And on the other hand, if you've got questions about material in lectures, make sure you ask. So there's only one really unforgivable sin here, and that's if you don't understand what's going on and you don't ask. And please don't be worried about your English. Yeah, you can send me an email if that's more comfortable for you. You've got my email address. You certainly should have it. Just drop me an email and ask a question, and we'll see what we can do to help you. Okay, so the whole process here is to try and get information to you guys so you'll understand what's going on. So again, here's my email address. It's fairly straightforward. It's john.sheridan@ucd.universitycollegedublin.ie, which is Ireland. Okay, and I mentioned sometimes this BRS. That's my consultancy firm. Okay, so I work in the School of Electronic Engineering here. I'm professor of optics, but I also have a consultancy firm, and I've started a couple of different companies over the years. Some have succeeded and some haven't. Now, I've got 4 references here to you. 3 of them are available. And this is to do essentially with the first part of the course. There's about 3 parts really to this course, as I would break it down. The first part has to do with the electromagnetic models describing the scattering that happens when one records holograms. And I find this very important. Maybe it's because I'm an engineer, but I like mathematics. And unless I've got a sort of a mathematical model that I can hang my hat on, then I really don't feel like I understand what's going on. So the physics and the mathematics help me understand what's going on. And then if I want to apply some of the ideas, I use those to help me figure out whether I can apply the ideas. So that's pretty much the first part. We're going to be talking about these models of holography. And there's several papers here. The first one I draw your attention to is this one by Hervé Kogelnik. This goes back to 1969. And in fact, a couple of the first lectures are going to be concentrating a lot on this paper. And there's a few reasons why I'm going to talk a lot about that paper. First of all, it would be widely recognized as a classic. And it pretty much has a very nice description of Bragg diffraction from volume holograms. It's quoted by everybody. It's referenced by everybody. The next paper I'm going to talk about is from Thomas Gaylord and Moham, and they had several papers, sometimes Moham and Gaylord. This is one of them. This goes to the 80s, so we jumped up here about 10, 15 years. And this talks a little bit more about the rigorous coupled wave theory. So they expand what Hervé Kogelnik to more rigorous electromagnetic numerical methods. The next one is a book. This is by Richard Sims. He was a professor. He studied in Oxford in the same group I did with a man called Laszlo Solomer. And then he went to Imperial College and he wrote this book. And this is from the 90s. And it's a very, very good summary of pretty much all the work that had been done to date up to that point. And it provides an overview and a standardization of notation. And I'm going to try in many cases to mirror his notation. So I strongly recommend that to you. And as I said, it's free, it's downloadable, and he's very happy if you download it now. And then the final reference is something up to date. Okay, so this appeared in 2019. I think it is 2018, 2019. It's by a professor, Raymond Kostuk. And he's a very nice gentleman. He works in Arizona. He works on holography, and recently he's been applying holograms to look at solar energy conversion. Now this, unfortunately, or fortunately for him, it's not free. You may be in your library. You may want to go out and get a copy yourself if you really, really see your future in this area. And that covers a lot of the more modern and recent things. Now I'll be sending you out some references as we go forward. So hopefully I'll be able to fill in any gaps. But frankly, if as part of this course you get through a few of these, you'll be doing very, very well. I certainly believe in the principle of overloading people with information, because in any real world situation, you're going to have a lot of information given to you and you're going to have to find your way through it. And I can recommend reading any of these. They'll be good for you. You'll learn a lot. As I said, it's going to be about 3 different parts. First part is what I'm going to do about now, and I hope by the end of this week, certainly we'll have got well through it. And that deals, as I said, with these models, electromagnetic-based models and structures, and how you differentiate between different types of holograms and different ways of talking about holograms. The second part is going to be about holographic materials, and a particular type of holographic material called photopolymers, because they're quite widely used. I'll mention some of the other types I've worked with, silver halide and dichromated gelatin, and even photoresist in my time. So we'll mention some of these, but I'm going to concentrate on photopolymers because they're very widely used. There's commercial products available, and frankly, it's the type of material I understand best. Okay. And then finally, we'll talk about something about to do with applications, but there'll be a certain mixture between all of these. So they're not really clearly delineated. I'm going to have to talk a little bit about material response when I talk about the models, electromagnetic models, and I'm going to have to talk a little bit about applications to illustrate what these things are used for. But I can certainly very strongly refer you to those first 3. And as I said, they're freely available. If you come across some book or some other reference yourself and you'd like to ask my opinion, I'm very happy to give that. So please ask away. Now, the first thing we're going to do is fairly light touch. I want to make sure everybody has a fairly reasonable idea of what we mean when we talk about holography, and particularly what I'm going to be talking about here. So the first thing is that holography generally involves 2 steps. There's a recording step, a fabrication step, an exposing step. They're all interchangeable names. And this here is supposed to be describing the recording of a hologram, and it's an off-axis hologram, and it's a transmission hologram. So there's a lot of terminology we're going to get through here, where we actually illuminate. We take light from a coherent source, a laser, and we collimate it, and we beam split it. And then we have a reference beam, which is a very simple beam, typically a plane wave. And then the other beam here, it hits an object, which generates a diffraction field, and the reference beam and the diffraction field overlap here in a sensitive material. And that's the recording process. So there's a couple of things here we'll just mention. One thing is the coherence length. When I started working in the area of holography, we had water-cooled argon ion lasers, and which could blow up. If the water switched off and it came back on again, the tube was so hot, the water would pour in and the lasers would blow up. Now, and the coherence length was about 10 centimeters. So you had to go around and draw lines on a table and make sure that the distance traveled by these two beams, the object beam and the reference beam, was roughly equal, because if the distances were different, then you would not get an interference pattern. Nowadays, you can buy a semiconductor laser, which is about the size of your hand, and it has coherent lengths of kilometers. And the other thing when I started was that these materials here, when you expose them, you then had to process them. And it was very much like the old photography. You had to go into a dark room and you had to mix up chemicals. And you can see that that would have led to a great deal of delay and a lot of mess. And some of the chemicals you had to use were unfortunately poisonous. And if you're working in the dark, it was often just simply hard to find out what was the difference between the glass side of a plate and the emulsion side of the plate. Nowadays, we work with photopolymers, and these are self-processing materials. And what that means is that when we shine light on them and we have an interference pattern, the material reacts to the interference pattern. And we don't produce some sort of a distribution, for example, a silver, which we then have to wash away. So we can go from something that looks like a black and white negative to something that's transparent. In these materials, when we shine light on them, they actually change with the light. We don't have to do any post-processing. Sometimes we may have to illuminate them with a beam to bleach out any dye in there, but essentially, once you've exposed it, it's done. Now, in the old cases too, when you had to process these things with water or liquid, you'd often get severe shrinking and swelling. And we'll talk a little bit about that later. I'll mention that, for example, there were materials called dichromated gelatin. And if you put them into the solutions, they could swell by a huge amount. In fact, they could end up looking like mirrors. Not perfect reflecting mirrors, they were diffuse mirrors, but they were very broadband reflective dielectric mirrors. So anyways, this, I said, is a recording, fabrication, or exposure step. And then we have the next step, which is a replay step. And what we see here is the big difference is that we have a stopper placed here. So we're no longer illuminating the object. And in fact, we've taken the object away. We've taken away the object. And so now what we have here is we have the replay beam, which is now incident on this static holographic layer. And if we view, if our head is down here and we look back up through this plate, we see a virtual object. We actually see the object. And if we move our head side to side, we're actually going to see this three-dimensional effect. We'll have a parallax effect. So if we had two objects here and one was behind the other, we could move our head and we could see the object that was behind the virtual object over here. We could see a change. And this is also the basis for holographic interferometry, or certainly some of the origins of this, in that, for example, if we kept our object in here, so we've made our hologram, okay, and the hologram is fixed, and we kept our object here, and we took away this stopper, we'd now have the field coming from the object, and it would come down here, and it would intersect the plate. We could leave a reference beam on. And what we would see here is we would see an interference pattern between the light from the hologram and the light from the object. So if we deformed the object, we'd see interference fringes, and we'd be able to see if this object was disturbed in some way. So for example, from this, we could figure out things like stress and strain. So as you see, even from the earliest days, holograms had very, very many applications. Now, what this leads to is it leads to nice holographic images. And we have, in the past, we've had some very nice collaboration with Biomaterial Sciences, which is now Covestro, and they produce rolls of photopolymer material. So these can be 100 meters long, and they can be 1.5 meters wide, and they can actually be polychromatic, which means you can record with many different colors in the layer. So typically up here in these diagrams, I've shown exposure with a single laser. In their material, you could actually have 3 lasers here, and you could be exposing the object with 3 different wavelengths, and you could be recording holograms with all 3 different wavelengths simultaneously. And here we show some examples from some of my graduate students. So when they want to make a present for their girlfriend or their mammy, they go away and they take some of this material and they make various holograms in various different wavelengths. And finally, again, when we replay, we don't have to replay with the same color we recorded. And in fact, we don't have to replay down here at the same angle for the reference beam at which we recorded. And we can talk about the replay conditions, okay? So the replay conditions don't have to be exactly the same as the record conditions. So this is the basis of a huge amount of work. And I know, for example, in Russia, there was a huge amount of work done on making holograms of icons and placing these all around in various museums. And the icons, because of the color tone, and many of them had metallic, so you had strong reflections from them, you could make very good quality reflection holograms. And so is all. Now, this is a bit of a cheat here. In general, if you take a photograph of laser beams, you don't really get anything. But there's all sorts of tricks. One of the tricks we've used is we've used fog. We've introduced fog on the table. And the other one is to do a very, very slow exposure, stick a piece of paper into the actual laser beam, and then move the piece of paper along the beams. And what you get basically is you get sort of like the dragged out pattern of the light as you move your piece of paper, which is a nice diffuse object. So it scatters lights in all sorts of directions. Now, one of the most fundamental things we're going to be talking about is this idea of a plane wave, okay? And I want to talk a little bit about this. Most of you have seen this before. You'd be very familiar with this. And I apologize to anybody who's bored. But part of this is the terminology and just making sure that everybody's at the same page. So we have this sort of generic type of description where we have these phase fronts. And the phase fronts are separated by a wavelength. So we could imagine this being two crests in the wave. And the wave is traveling in this direction given by the k. And this k vector, we talk about the wave vector. And it is 2 pi divided by the wavelength. If we're in free space, that's the wavelength in free space. If we're in an isotropic material, it will be 2 pi times the refractive index, n, which is the square root of the relative permittivity, divided by the wavelength. And of course, this is actually space. So the units along this axis are meters in x and meters in y. So we've drawn this vector here, but that vector k per se is not in that space. We're just indicating a direction, and we're indicating that that plane wave, this is perpendicular to the phase fronts, and it's traveling at some angle theta with respect to x. As we said, these are separated by the wavelength, and we note that in this direction here, we have a projection here of the wave fronts here in the x direction, and that's going to have a distance which is given by 1 over fx, and fx here is our spatial frequency. So just as we have time, we have a time axis and we have a frequency axis, and time is seconds and frequency is 1 over seconds or hertz. In space here, we're going to have position, x and y, and we're also going to have a spatial frequencies in x and spatial frequencies in y. And here's the actual description of those things, or indication of what these things mean in the actual xy space. And we're going to be differentiating between this position space and this k space or phase space as we go forward. In particular, we're going to be talking about a thing called the Evil diagram, which is very handy. It gets you to appreciate a lot of what's happening in relation to holography. So these parallel dashed lines represent lines of equal phase for this function. And this is how we generically describe these plane waves. And again, we've got 2 pi times f of x, and 2 pi times f of x is equal to 2 pi divided by the wavelength multiplied here by a cosine, and the cosine of that length theta. We have a wave phase front. Plane waves, we then notice, are modes of free space. So we can take this and we can substitute it into the electromagnetic wave equation, and we find it's a perfect solution of the electromagnetic wave equation describing propagation of electromagnetic fields in isotropic space. In fact, there's only 3 solutions. There's the plane wave, there's the spherical wave, which we meet when we talk about Huygen's principle, and also there's the cylindrical wave. All of those are exact solutions. Here we're talking about the plane wave. That's the one we're going to use most commonly in relation to holography. Now, again, if I say anything here that worries me, worries you, please just interrupt and let me know, and I'll come back and I'll cover this again. I'm going to repeat some things a few times, especially in these early lectures, because as we go forward, we're going to be dealing with much more complicated things. And if we've got the basics right, you can hang your hat on something you definitely know, we'll all do much better. Now, we have this k vector here shown as a ky component in x and a component in y. And the magnitude, of course, is going to be the sum of the squares, the square root of the sum of the squares of those magnitudes, those components in x and y. And again, if we're in free space, for example, we sometimes write that magnitude as beta, as phase constant, which is 2 pi divided by the wavelength in that space. And again, if we're free space, air is very close to vacuum, and that would be the free space wavelength. If we're not in free space and isotropic, then we'd multiply this by the refractive index. In other words, we divide that wavelength by the refractive index. And again, we note that if we go from one material into another, the frequency never changes. So if we've got radiation traveling, for example, from air into glass, In both air and glass, it has exactly the same frequency. The color of the light doesn't change. The energy in the photon doesn't change. However, the wavelength will change. We'll have a change in velocity. And of course, our frequency times our wavelength is our velocity. So if the frequency doesn't change, it's the wavelength changes and the velocity changes. They're both divided by the square root of the relative permittivity, the refractive index in that medium. So these plane waves, as drawn here, are infinite extent. They go to plus and minus infinity, okay? And the frequency domain, they are therefore completely localized, okay? So if we have a plane wave and we find out what the Fourier transform of that plane wave is, so we find out what representation we have of that plane wave in frequency space, then we find we have a delta function. All the energy is localized at a single frequency. Now, you might come and you might say, well, this all sounds very dodgy because in physics, we don't have things that are infinite. Yeah, we don't have lasers that have a single wavelength. There's always some bandwidth associated with the frequency of the wavelength. So with the frequency that comes out of a laser simply because of thermal effects. And that's true. We may have an output frequency, which is hundreds of terahertz, but we're always going to have a megahertz of bandwidth associated with it, which is absolutely true. But it turns out we're very well used to using concepts like this, certainly in electronic engineering. We're very happy to use sines and cosines. And of course, a sine and a cosine is something which is infinite. A sine starts at minus infinity and ends at plus infinity. So we use these sort of things all the time. It turns out they're very, very useful. We use Fourier series and infinite series expansions. So we're actually really quite comfortable using these infinite things. And it turns out they're very, very useful. We certainly can find them and we can apply them, and they give us very good insight to what's going on. So we don't have to worry about this too much. So one of the things you should be picking up here is that I'm not going to do a lot of very, very rigorous proofs. I'm just going to appeal to your good sense as an engineer, okay? So we note here that we have this plane wave traveling up here in this positive direction, and we note that the spatial frequencies associated with that are going to be positive in both directions. And if the plane wave was traveling in the opposite direction, was traveling downwards, we'd have negative spatial frequencies. So we see there's a sign associated with the direction, the components of the actual K vector. Okay, so we'll take a breath and we'll take a sip. Now, the first way you generally learn about holography is this way that I'm going to talk about next. And it has to do with this idea of illustrating. Usually it's introduced to illustrate things like off-axis, the advantage of off-axis recording. When Denisuk first produced holograms, he produced them for a non-axis arrangement. So his interference beam, if we pop back up here for a second, his reference beam and his object beam were both traveling in the same direction. They weren't separated by any angle. So typically what he would have done is he would have had his light and he would have had a transmissive object and he would have taken the light here and there would have been no beam splitter. In fact, his object would have been here and his holographic plate would have been over here. And he would have sent light through the object. And basically some of the light was scattered by the object and some of the light just went straight through. And what he did was he recorded the interference pattern between the light that went straight through and the light that was also scattered by the object that the light had gone through. And there were severe problems with that. You had all the various beams. If you replayed it, you had a lot of different beams on top of one another. Now, of course, in fact, Denisuk was actually trying to record effects with X-rays and replay them with light because he wanted to not only get the phase information and the amplitude information, but he also wanted to get out the holographic information and the magnification effect by replaying with the light. You can go back and look at the original paper. It's actually quite short. And he wasn't going to use, he didn't have access to lasers, for example, okay? But typically this is the sort of way people describe holography when you meet it first. And they'll tell you that a photograph is essentially a two-dimensional view, X and Y of a scene seen through a pinhole. So of course, if you move your eye away from the pinhole and you don't get any three-dimensional depth. You have no depth information regarding the field is stored in a photograph. A photograph contains no phase information because most materials, most detectors and most materials, in fact, all they do is they measure intensity. They don't measure relative positions of photons with respect to one another or wavefronts with respect to one another. You typically have to have some reference, yeah, some reference in order to do that. So you typically have to have some sort of an interference pattern. In any case, A photograph contains no phase information. The incident field, only the amplitude, the magnitude squared of the electric field, is captured. And there's no new information stored in the volume, the depth or thickness of the photographic emulsion. So pretty much if you've got a black spot on the surface, the black spot goes all the way through any sort of a depth that you've got in your photographic emulsion. A hologram contains a view seen through a window. So this is the crucial difference. You've got a pinhole for a photograph, you've got a window for a hologram. And so the hologram contains parallax information. So information regarding the relative position of one object with respect to another. Now, as I read this, I sort of, unfortunately or fortunately, I have all the context of work that people are doing now. So I have all the information about things like digital holography and iterative phase retrieval in my head, or multiple step interferometry, okay? But we'll come and we'll talk, maybe we'll mention some of these things, but as it stands, this text is pretty much accurate about what we're talking about. As you move your head, your point of view varies, and in this case, you can see one object behind another by changing the relative view position. In a holographic emulsion, an interference pattern is stored in the volume. So you've got an interference pattern, you've got variations of the amount of light in 3 dimensions inside that volume. So you can imagine you've got an interference pattern varies in X, Y, and Z, and these interference pattern, this intensity variation inside the material is going to produce different effects at each one of the 3D points within the material. Unlike a photographic emulsion, not only is the incident field or amplitude information captured, but it turns out you're also capturing phase information. Although the material is only reacting to the intensity, because you've got the reference beam in there, the pattern you've got, the intensity pattern you've got, has actually stored information about the relative phase between the reference pattern and the actual object field. The objective of holography is to record for subsequent reconstruction a complex amplitude and phase wave amplitude distribution. Special techniques are required since all optical detectors, including film, only respond to wave intensity. And photographs record the image incident on a film, but without holographic techniques, it's impossible to record both magnitude and phase of an infinite field. So we can think of our field as a phasor. We have an amplitude, and perhaps the amplitude varies as a function of X, Y, and Z. And we also have a phase, and the phase can vary as a function of X, Y, and Z. Holography is a 2-step process, as we've mentioned above. The first step is referred to as interference or exposure recording, involves a fabrication of the hologram. The second step, referred to as reconstruction, replay, or diffractive step, involves the recreation of the exposing field. And in the first step, an object field is interfered with a reference field to form a 3-dimensional interference pattern in a space containing a recording medium, so a plate. Or nowadays, we have cameras, and you might say, well, a camera only captures information in a plane, but we'll talk maybe a little bit about that later. But let's just pick with our volume at the moment. Typically, the reference field is simple. It's easy to reproduce, so it may be a plane wave. It's not, all it's doing is being collimated and coming straight from the laser. But it doesn't have to. It could, in fact, be more complicated. Many people use, for example, spherical waves as a first step, but it could be something else. It could be, for example, a key, which is encrypting the data in the hologram. In the second step, the recorded or fabricated 3D interferogram, the hologram, the diffraction grating, is replayed by a suitable duplicate of the original field. Now, a certain amount of what I'm going to do here is just I'm going to use all these different words, and you might say to me, well, look, if I know one word, that's enough. The problem is that lots of people write lots of papers or books, and they tend to use different words. And if you can imagine people making holograms in the visible, and other people making holograms using neutrons, which they do, or making holograms using X-rays, well, the point is people use different terminology. I think we all are familiar with polarization in optics, and the number of different ways you can talk about polarization. You can talk about E mode, you can talk about S, you can talk about TE, you can talk about fast, okay? And all of these things mean essentially the same thing, but they're used in different contexts. So knowing the terminology, the language, is quite important so that you've got a clear understanding what's going on. And if at any point I use some terminology or use some words you don't like, you've got to let me know and I'll try and clarify. Anyway, a reconstruction of the original object field is then produced by diffraction. You replay the hologram. A properly positioned observer can then see the object just as though it were present. This is the virtual. It's not there, but we can see it. Since this, I see a duplicate of the original field at every location from every viewing position. Now, of course, I say the hologram is like a window, But generally in a window, you can see things from a variety of very extreme angles. And often because of material response, we are not able to reproduce every viewing angle of the object. There's some response to the material. So you can imagine that we're trying to record all of the high frequency information, but the material is like a low pass filter. It'll only record some of the spatial frequencies, some of the interference patterns. And if the interference pattern gets too high frequency, the period becomes too small, perhaps the material doesn't react as strongly. So we don't get necessarily all of the viewing angles. So holography was invented by Denis Gabor in 1948 in an attempt to improve the imaging of electron microscopes. And with the invention of the laser and the off-axis geometry of Leibniz in the early 1960s, the hologram in holography became practicable. Now, again, we note that Leibniz didn't have a laser, certainly not initially. They were using things like Gabor, which were like mercury lamps. So they had a narrow wavelength band, and then the radiation came through a pinhole. So it was weak, but they could ensure some coherence. But the advent of the laser and the advent of off-axis geometry, as we'll see, greatly enhanced the capability of seeing very nice images with the holography. And sort of that was what intrigued people most, and still does to a certain extent. Holography and holograms find many applications in the areas of data storage, metrology, so deformation measurement, I mentioned this earlier, pictorial art, signal processing, okay, sideways looking radar, optical elements, the production of holographic optical elements for beam splitting and beam shaping, lenses. So for example, if you think about a big refractive lens, it's big, it's thick, it's bulky, you can produce a lens in a very thin layer, and it would certainly work reasonably well at a single wavelength. But again, you have issues like you have with lenses to do with aberration. And if you will play at a different wavelength, you're also going to have chromatic effects, because these are dispersive elements. They're diffractive elements. We'll talk a little bit about that later as well. So active areas include X-ray, neutron holography, and holographic real-time TV. So this is a very heavy area. People have been working, they've been trying to produce three-dimensional images for a long time, okay? And now they're trying to produce holographic displays with mobile phones and augmented and virtual reality devices. And even people have produced contact lenses that you pop into your eye and give you this three-dimensional view. So there's a lot of very exciting things happening out there. As part of this course, there's also talk about holographic data storage, because you store a lot of information. You can come back and just look at this entire process as a process of storing information in the layer. And basically you have, instead of a pixel, you have a voxel in the volume, and you produce a field, a three-dimensional field. So you can get very high data densities. And of course, the beauty is if you shine light on the plate, you get out that data and there's no wear and tear. Turns out, sadly, like everything in life, it's a lot more relatively talk about things very difficult to do. But if you work hard enough and long enough, it's amazing what you can achieve. So let's talk a little bit about this off-axis holography. And so we have our object, we have an illumination beam hitting the object, and this field here, this distorted field here coming in and interfering at this plate with a reference beam. And we can assume that the illuminating beam and the reference beam are both coming from some source. So you've got this interference pattern. And what we've done here is we've got this angle between the reference beam and the object beam. So the object produces a complex wave field distribution, A of xy. This is the object wave. It's incident on the photographic film, the medium. Incident simultaneously is a plane wave at an angle theta with respect to the normal, and that's going to have a distribution which looks like this. So here what we can see is we've got a plane wave with a constant amplitude. So this here is a constant amplitude plane wave. And typically we're going to vary the amplitude in that plane wave, and we're going to vary that amplitude so that we get the highest contrast in our interference pattern here at the recording material. So if this becomes too big, we're going to have a large amount of power coming in on that reference beam, and our interference pattern is going to be, if you like, floating on top of a large DC value. And if our material reacts to the radiation, then what's going to happen is that a lot of light will come in on the reference beam, and it will be using up the sensitivity of that material. So in fact, it'll just be changing the average index. And what we want to do is we want to modulate the refractive index, for example, here, if we want to have a phase object. So the interference pattern is going to lead where there's high intensity, maybe to a high index, and where there's a zero, where there's a destructive interference, we're going to produce nothing. And we don't want to just be producing average index. So we don't want to just have a big, strong beam coming here, changing the index everywhere by the same amount. We want to use, or we want to modulate the material we've got in here. We'll talk more about this sort of an idea later. We're going to start off fairly simple. So we have the object beam, which is complicated. We have variations in the amplitude of the phase everywhere. And we have this reference beam, which is very, very simple and is coming at a particular angle. And that angle is going to define our spatial frequency. We've got this sine theta divided by lambda. Assume the amplitude A is real valued, then the total field in the plate is given by this. It's the sum of the two fields. So we have the sum of the two fields, and the sum of the two fields is what we've got in here. The intensity is the magnitude squared of this, which is going to be this multiplied by its own complex conjugate. So we have a corresponding optical intensity given by this. So we have an A squared here, so we have this multiplied by its own complex conjugate. And we've got this, the object field, multiplied by its own complex conjugate. And then we have these cross terms. We have the cross terms. And we can see that these are traveling with different, they're multiplied by these different spatial frequencies. Okay, so they're effectively shifted. Yeah, they're going to be shifted in angle. They're going to come out, or they're going to be present in the thing. So we haven't talked about replay yet, so let's just leave this for a second. But we also notice here that we have the actual object field here. We've got A times the small a, which is the object field. So this is the thing we want to get. We also have A here multiplied by the complex conjugate of the small a. So in this interference pattern, we see that embedded in here. We have stored inside that material, we've stored in the actual field here. And of course, the point is, this is intensity is a real value. And we see we have the sum of two things here that are a complex conjugate of one another. So of course, when we add these two together, we're going to get a cosinusoidal interference pattern. Okay, so we haven't done anything weird and wonderful. We just note that this is actually encoded, encrypted into the material. We can write this in the magnitude form. And if we do that, we see that it is real. We see we've got everything is magnitudes, and we've got this cosine. And the cosine in here has got this phase term associated with the object, the magnitude of the field and the phase of the field here. We've got this phase modulation on our cosine here. And that A is given by, the A is complex, it's the magnitude times this phase term. The third term in this expression, the third term here, contains information about the magnitude and the phase of the object field, though through the modulation of the spatial carrier. So this modulation in here. The incident intensity is recorded in the photographic film in such a way that variations in the wave amplitude transmittance of the film are proportional to variations in I of x. So what's going to happen here, and we're going to make a little jump here, I'll come back and talk about this later, but we're going to assume that we're going to have some incident field on this, and that incident field is going to be multiplied by this. And so the field that comes out of this, we could imagine, for example, this produces a modulation of the intensity, but the field that comes out of it is going to be scattered by this, is going to have this information embedded in it. Now again, there's a couple of little leaps here, and hopefully we're going to put this in some context later. We're going to talk about transmittance functions a little bit, and we're going to talk about electromagnetic models of holograms. But for now, this is nice and plausible type of a description of the operation of a hologram, and it illustrates a couple of important things about holographic operation. We return to our discussion of photographic film and the characteristic functions relating the amplitudes. So I say return here, we just talk about how the material is going to react. And typically with the old-fashioned films, you had something like a TE curve. And it looked often, you had something which looked like this, where, for example, you produce a negative, you get a certain amount of transmission from the actual plate. And it depends on the exposure energy. And you had some sort of a characteristic like this. You had to expose above a certain amount, or you got nothing happening. And by the same term, there was a linear region in here. So if you put a sinusoidal interference pattern in, you would record a sinusoidal variation of the modulation of the material. And if you came over here, again, with too much energy, you basically got no effect. You got saturation, for example. But there was a linear region here. And this is very much a nice, simple material model, which says if I've got an interference pattern in, and it has a certain maximum intensity, a certain visibility, then there's a certain region where I can record. And I can record linearly. So the variation in the material properties will be linearly proportional to the intensity exposing. And as I said, the visibility is going to depend on the beam ratio. So we assume that we restrict ourselves to this linear portion, And again, we're not too worried here about spatial frequency. There's also a spatial frequency response, but let's assume that we have an intensity, an amplitude of the intensity variation, and a frequency so that we get a nice linear response from the material. We restrict exposure to the linear portion of the curve. We have a linear mapping of intensity variation transmittance function is achieved. And this transmittance function describes the light that gets through the photographic plate. Proper exposure is achieved by controlling both the exposure time, or the dose, so we talk about an exposure dose, and the ration of the ratio of the object beam amplitude to the reference. So this should be ratio. And what we do simply is we say, well, okay, the transmittance function, okay, and we're going to talk about what we mean by a transmittance function, but in the simplest level, the transmittance function is the ratio between the field that comes out divided by the field that goes in. And we assume that our photographic film is infinitely thin, which seems to contradict this idea of recording a volume object, but we'll stick with it for the moment. That our transmittance function associated with this is given by the interference pattern multiplied by some constant, and that constant is associated with the slope of that material response. Okay, so we've got this very simple idea. We're not worrying too much about depth. We've only got this thing as a function of x and y. We haven't mentioned z. And we talk about this being the transmittance function. So if we want to find out what comes out from this object, we're going to replay it with a plane wave. So we multiply this transmittance function by the input field, and it gives us our output field. As I said, this is the ratio between the output field divided by the input field. So in the reconstruction process, the hologram is illuminated by a plane wave incident at the same angle as the original reference wave. So it has the same wavelength, it's incident at the same angle, and we represent this by a new plane wave. So now we have B here, just to differentiate it from the recording reference beam. And we're going to multiply this field by the transmittance function to find our output field. Okay? So we multiply this here, we multiply it by this, and here we've got a constant, so we're just going to get this coming through, some factor of this coming through. And then we're going to get a series of things which are the light that's going to be diffracted. Okay? And if we multiply across and we use our full expansion, we don't use the cosine, what we find out is we have these four terms. And this term, this is the most important term. This is a constant times the object field. So we've reproduced the object field. And we've got a range of other terms, and each one of them may have a different spatial frequency modulation. So this is the 2 pi f0, 2 pi f0. Here we've actually got 4 f0. So this is going to be coming out at a bigger angle. So we got 4 terms. The third term is within proportional constant, a duplicate of the original object field. So this illustrates the principle of holography. We can reproduce this field. The first term is a plane wave propagating in the original incident direction. The second term is a modulated wave also traveling in the reference wave direction. So these are messy. This is fairly straightforward. It's a plane wave. This is messy because we see, look, we're going to have superimposed on it this amplitude, which is varying as a function of x and y. And the fourth term is another modulated wave. You can see here it's multiplied by the complex conjugate of A. It's traveling, however, a bigger angle with twice the spatial frequency of the reference wave, which means it's coming out at a bigger angle. So what do we have? We have our reconstruction. We have our observer here. So this is the one we want. This reproduces the field that comes from the object. We have transmitted light that comes straight through, and then we've got another beam which is coming here at twice the angle. And again, if we go back here to our exposure, up here, we see here, this is our object, and now we're looking in here and we're seeing that complicated field from that object as though it came from that object source. So that's our basic holographic principle. And it's fairly nice, and it explains a lot of things. So if you go and make holograms in the lab, this is basically going to be the type of arrangement in general you're going to be using. What Kogelnik did, what Denisuk did was, he would have had the object in line with the reference beam. So when he looked into his holograms, all of these different beams were on top of one another. He saw all of these things superimposed on one another because he used an inline geometry. Now this again is a transmission geometry, so the replay is on this side and the reproduced field is on the opposite side. Denisuk produced holograms where the reproduced field was on the same side, so you illuminate it from this side and you looked at it from this side over here. And it has particular characteristics. We'll talk a little bit about these characteristics later. But essentially, it turns out that reflection holograms are very wavelength selective. So if you shine white light in them, typically they only reflect one wavelength. So you can replay them. You don't have to replay them with a laser. You can replay them with a broadband source, and what you'll see is a single color. They're very wavelength selective. On the other hand, transmission holograms are very angularly selective. If I change the angle of the input beam, I'm going to lose my object. I'm not going to reconstruct the object. Okay, I'll see rainbows. Now, again, this is all about terminology and getting used to these words. And talk about two types of holograms. The transmission hologram I just spoke about. Here I record, we've got two beams on the same side, and here I reconstruct, and I get a transmitted beam and a diffracted. This is wrong, excuse me. This is the transmitted beam, and this is the diffracted beam. Okay, so this is the transmitted beam, and this down here is the diffracted beam. The object and reference beam are both incident from the same side. Replay produces two beams on the opposite side during reconstruction, and these gratings are highly angularly selective but not wavelength selective. So if I change my replay wavelength, I still get a diffracted beam coming down here. But if I change the angle, typically the amount of light in the diffracted beam is going to disappear. And then Denisuk worked with reflection gratings. And I show here now, this is an example of an unslanted transmission grating because the angle between these two beams is equal and it's to the normal to the surface. So I actually end up with fringes, an interference pattern and fringes which look like this. All the lines here are parallel to one another, and you can see they're all perpendicular to the boundary. This is a case of an unslanted reflection grating, which is very much like a dielectric mirror. It's like a dielectric mirror. And in this case, the reference beam and the object beam are on opposite sides. And if I replay here with the reference beam, I get the diffracted beam backwards here in this direction and the transmitted beam over here. So over here, I'm going to see the object, virtual object up here. So at least I've labeled these correctly here in this diagram. That's the diffracted, that's the transmitted. This is diffracted and this is the transmitted. And they're both unslanted. Again, because if I look at this, we see we have the same angle here to the normal as we have over here, but they're now counter-propagating through the material. Now, of course, in this case here, we've got to be a little bit careful because when we put light into these materials, yeah, we have an intensity. And essentially that intensity is going, that light power will be absorbed during formation or of the recording of the material. So typically, if we could imagine measuring the intensity at different points with depth, because of the absorption due to the dye, the actual interference pattern will get weaker. The amount of intensity exposed in the back here will be less than the amount of intensity exposed in the front because we have this absorption. And so we'll actually get some variation in the modulation with depth. And the same thing here. Yeah, this is even more complicated. We're going to have some very unusual cross-section between these two things. Typically, we may have a maximum in strength somewhere here in the middle, but we'll talk about that again a bit later. The optical nerves are incident from opposite sides. Replay produces two beams on opposite sides of the hologram, and these gratings are highly wavelength selective and sometimes referred to as white light or color holograms, since they can be replayed with ordinary white light, but a clear image in one wavelength is seen. And you can change, you can record with certain wavelength, and if you want on purpose, you could actually shrink or swell this in a uniform way, so you could record at green and then replay with white light and see actually a picture in red. Again, these are monochromatic type situations. And as I said, there are polychromatic devices, materials available now. In these examples, only plane wave reference illumination was being discussed. And as I said, it turns out this idea of plane waves, gratings recorded with plane waves, first of all, you can learn a lot by studying what happens in those cases, but also the plane waves, you can take any field in free space, and by applying a Fourier transform, you can split that up into a spectrum of plane waves. And since the plane waves are the eigenfunctions, they're the modes of free space, it turns out that's a very handy way to describe fields as plane waves. So you can talk about things, and of course, if you get two plane waves, they will interfere. It can be called sinusoidal effect. So we can talk about spatial frequency response materials. So the plane wave and plane waves interfering with one another are very important ways to characterize what happens in these materials. Spherical illumination is also possible, and in many cases preferable, as it is easier for practical reasons to implement. Basically, the output from a laser is more or less a spherical wave over some extent. Furthermore, any object can also be thought of as made up of a spatially distributed array of point sources. So this is our Huygen principle. We can take the field in free space and we can write it as a whole set, an infinite spectrum, distribution of plane waves. But we can also describe any field as being an array of point sources for spherical light beams, like Huygen uses to describe the propagation of wavefronts. Now, another type of hologram, which you'll hear referred to, is this idea of the rainbow white light transmission holograms. And if you've seen holograms regularly, they've probably been on your credit cards. And those are essentially rainbow, white light transmission holograms or reflection holograms. And essentially, instead of recording light from a plane, okay, from a light source, which is a point, what you actually do is you record using a beam, which is either from the object and or from the reference, which is through a slit. Okay, so instead of these nice plane waves, you're going to do something which is slit. You take a slit view. Now you can imagine if we look through a point, we see a point view. We have no depth. If we look through a window, we have our three-dimensional depth. If we look through a slit, we're actually going to get parallax in one direction, but not in the other. And it turns out the way humans actually look at the universe, we actually tend to have much more of a view in the horizontal than the vertical, just the way our eyes actually work. And it turns out, therefore, there are some advantages to this rainbow, particularly in terms of the response to the material and using the material, as, if you'd like, in a particular direction. There's also an attractive feature, or at least something that humans find attractive, in that if we look in the direction, we have the depth in one direction across the slit, but in the other direction, we're going to still get dispersion, and what we get is a rainbow effect. So these are very, very colorful. And it turns out one of the reasons people like to use holograms is because they offer security. They're relatively hard to counterfeit. Holograms are hard to counterfeit. And there's many stories. One funny story was the euro note, the 500 euro note. They used holograms for security. And there was a story that in Italy, in fact, the mafia decided to print their own 500 euro notes, and they released these notes before the real EU money was sent around. And the one thing they couldn't counterfeit was the hologram. But when the real notes came out, people didn't believe they were real money because they'd been using the previous money, which was simply a form of photocopying. But holograms, it turns out, are useful for security, and people even talking about putting holograms on to individual tablets and pills because there's a lot of fake medicine out there. Anyway, if instead of making a hologram of an object through a window, a transmission hologram is made of an object seen through a slit, two significant changes take place. First, parallax is still available in one direction. One, for example, can still move your head side to side and see behind an object. If a white light source is used to replay the transmission hologram grating, dispersion takes place. In other words, the incident light is diffracted at different angles depending on its wavelength. The result is that the same image appears with different colors. You tilt it and you'll actually see the same image, but with different coloring. However, instead of these images lying on top of one another, so again, now, just to be clear, this would be a monochromatic recording, but you're replaying with white light. So you're not actually seeing the true color of the object. You're simply seeing the same image, the same field replayed with different wavelengths. However, instead of these images lying on top of one another, because of the use of the slit during recording, they appear above and below one another and can be viewed separately. In other words, in the other direction, up, down, a rainbow of images can be seen. And the rainbow hologram was invented by a fellow called Steve Benton, who worked at MIT in '69. Rainbow holograms can be mass-produced using simple copying techniques. And so on the credit cards, you actually see something which is embossed with some sort of tin foil. And embossed reflection hologram creations are widely used on credit cards and for security purposes. Okay. Now, we're pretty much at the hour point. We're coming up to the hour point. And at this point, I'm saying to you, well, okay, what have we done? Well, we've introduced our holographic principle and sort of the general way people talk about holograms. We've introduced a little bit about material characteristics, and we've shown you some sort of basic examples. We've talked a little bit about the history of the holograms and holography. We've introduced our plane wave, and we've shown you some examples, okay? So these are all the basic things and the basic notation and ideas you're going to need to know here. So hopefully now you can go through that yourself and you can figure it out. And if you go and look, for example, at the Sims book, you'll see he kind of starts off, he talks a great deal more about these things and gives you a lot more background, but basically those are the sets of ideas he introduces. And they're critical, whether you're talking about holographic optical elements or holographic data storage or holographic interferometry, all of these things pertain. Okay, so I mentioned to you this idea of plane waves and why they're important. And in fact, most of the devices that people use, or well, maybe it's dangerous to say most, but very many of the holographic optical devices they use are holographic optical elements. They're volume holographic optical elements or components. And some of the simplest of these and some of the most useful are things like beam splitters, where what you do is you record a cosinusoidal interference pattern and you produce a cosinusoidal variation of the material parameters, the absorption or the refractive index. A very important point here, though, is that, again, what I said previously is that these cosinusoidal variations, if we can find out how the material records these cosinusoidal interference patterns, we can change the amplitude of the cosinusoidal pattern and we can change the spatial frequency of the cosinusoidal pattern. And using this, we can characterize the material. We can find out how the material responds for different intensities and for different spatial frequencies. So besides the fact that you can actually produce a range of holographic optical elements which are useful by recording cosinusoidal interference patterns. So for example, you can record beam splitters, you can record dielectric mirrors, you can have devices which can be used to couple light into and out of waveguides, for example. Besides that, you can also use this process to characterize the material. And then finally, there's a lot of complicated things that are happening inside the holograms. In many cases, it's the same thing happening over and over again. But in order to describe them, you want to start from the simplest picture to get a clear view of what's happening. And then basically things are going to get much more complicated. Yeah, they're going to get much, much more complicated. And part of this is going to be trying to discuss this by describing all these different models and all the different types of effects which happen in the materials and which are best, I think, discussed in terms of the actual electromagnetic models used to describe what's going on, starting with Coherence. Okay, so we've got this system where now what we have is we have two beams. We have a laser beam here, which is going to be the exposing. And we've got this here shown. We have the light comes out. We have a beam splitter. We split the light into two parts. These two parts interfere inside the layer. And we have two detectors here. And these two detectors are measuring the transmitted light of the exposing beams. And as I said, some of this exposing light is going to be absorbed by the dye in the material. And by monitoring these two beams here, we can get out some information about what's happening as the material is absorbing dye, or we can even use much simpler systems where we simply expose the plate by a single beam, and we see if we can understand what happens with the dye. In this particular arrangement here, we also have a probe beam, and the probe beam is at a different wavelength. It's at a different wavelength. It comes down and replays this grating, and we can choose. We mentioned previously that we can record and we can replay at different wavelengths. Well, we can choose this beam to replay this grating on Bragg. I'm going to talk about what that means. But essentially what it means is that we're going to get a sizable amount of the light diffracted by the grating as it formed. And again, we can measure the transmitted light there and we can measure the diffracted light. And so again, we're going to get information about how the actual grating is being formed using light which does not interact with the dye. Okay, so we're assuming that this beam here is only going to interact with the refractive index modulation caused by the interference pattern or by the absorption pattern. And at the same time, we can have this nice cosinusoidal interference pattern. Yeah, we can take this plate and we can have this plate attached to some system like this, where we can translate in X and Y. So for example, we could do multiple exposures on different parts of the plate. But we can also have it on a rotation stage. And so for example, if we turn off our exposing beams, we can rotate the hologram and see how this diffraction efficiency changes as we rotate the hologram. And if we get that, we'll get some selectivity. And we're going to talk about thin gratings and thick gratings. And the big difference is that for a thin grating, we have no selectivity. So if we rotate the grating, we don't change the amount of light diffracted. But in a thick grating, or where we've got a Bragg response, as we rotate this, as we change the angle of incidence, we're going to move off Bragg. And for this transmission type geometry I mentioned previously, that our transmission gratings are highly angularly selective. Okay. So
Excuse me, Professor Sheridan. You
Yes.
asked to tell you that it's been an hour of lecture,
Okay.
so you want to break.
Okay. So does anybody want to go to the bathroom or have a quick drink of water? Maybe we stop for a minute or two. Okay. Just stop for a minute or two. As we're waiting here, has anybody got any questions about what we've been doing so far? Good. Everybody understands everything perfectly.
Yeah, it's been pretty clear so far. Thank you.
Very good. Very good. Now, as I said, I understand you're going to do some labs. I know some of these are going to be computational. And hopefully, again, as I said, we're going to have a good, the language is going to be clear and you're going to be able to understand what I'm doing. Because as I said, as I move forward, I'm going to assume that you understand all these things I've been talking about. Well, you may not understand them, but at least you're familiar with them. Yeah. So I'll be able to talk about exposure and probe beams and all this sort of thing, replaying with different wavelengths, transmission and reflection geometries, and you don't have a very, very clear idea of what these things are.
Actually, I want to mention that if you have questions, you also can ask them in the chat. And after the lecture, we will read all the chat questions and
very
Professor
good.
Sheridan try to answer them.
Very good. That's very good. Yeah. I'll make sure there's some time at the end for people to do that. Okay. And this is, again, as I said, the main issue now is not per se the difficulty of concepts, okay? It's just familiarity with all the background material and familiarity with the language of people in the area. So you'll be able to talk to people who've done this type of work before. So wait one more minute and then I start again. I really probably cannot stress enough how important it is for you to have other sources of information, okay? And that's particularly those 3 open access papers that are given above. And as I said, there are several books out there published in the last 5 years or so about holography. I think the Acoustic one is particularly good. But if there's any issues here, I think it's always good to read other people's opinions about things. Sometimes you find a particular author who expresses things in a very, very clear way. And if you can find somebody like that, who, you know, that they're writing it and you're understanding it, that's very good. Because unfortunately, or fortunately, there are many different styles and there are many different ways to describe things. And so it's very important to try and find somebody that you're used to or you like. Now, I haven't attempted to give the references for any Russian authors. I'm sure your lecturers over there will be able to give you access to information in Russian. Yeah. And I'm sure that in most cases, the terminology will be quite similar. So again, that's also a very good avenue for you to pursue. There are certainly very, very excellent people in Russia. I just would not be familiar with the literature in Russian. Okay, so we start again. So this type of grating, cosinusoidal exposure, is going to produce a sinusoidal variation of modulation. And we talk specifically about a Bragg grating, a volume Bragg grating. And again, we have this idea of the 2 beams. In this case, the 2 beams are not incident with the same angle. So we got a θ1 and a θ2. These will be 2 plane waves. And in that case, if we look at the interference pattern, what we find is that it's going to be tilted. Typically, what you can do is you can draw a line down the center between these 2, and you'll get a cosinusoidal variation, which will be aligned, the fringes of which will be aligned with the angle, the line which bisects these 2. In terms of, and this would be called a slanted grating. Okay, so previously we talked pretty much about unslanted gratings. And when we do our models, we're first going to look at models of unslanted gratings, and then we're going to look at models of slanted gratings. In this case, if I replay with this beam, I'm going to get a transmitted beam and I'll get a diffracted beam. So we have a recording and we've got a replay of slanted transmission gratings. And in this transmission geometry, in this unslanted case, we've got a set of mathematics notation that we're going to be seeing over and over again. So we're going to come back and we're going to meet this a number of times. And some of these slides I'm going to repeat just to remind you. But we're going to have here that we've got these 2 equal. And so we've got the fringes here where they're perpendicular here to the boundary. Yeah, they're parallel to the axis here. And we've got an input, a transmitted and diffracted beam, I sub d. And we've got the x direction here, and our thickness direction is z. And we've got a layer with a certain thickness d. And we've got a period. There's a period associated with these fringes, the interference pattern. And we've got a capital K. So this now is not the same as a small k. And this capital K vector is pointing perpendicular to these fringes effectively. So we have only a component in the x direction. And we recall the small k was 2 pi divided by the wavelength. Well, this capital K is 2 pi divided by the period of the grating. And it's called the grating vector. This is the grating vector. And this has got a component in the x direction. And we can write the refractive index modulation, the variation in this material, and we assume there's no variation with depth now. We have a uniform variation. We've got a cosinusoidal interference pattern, and it produces a cosinusoidal variation of the refractive index inside this layer at every position here in D. And it's an average index plus a modulation of the index times a cosine of this K, this grating vector, dot R. In this case, it would be equal to Kx times X, where X is along this direction here. So again, this is introducing notation. Yeah, the mathematics we're going to be seeing, and we're going to be seeing these things several times, and we're going to be deriving things. But we notice that typically people talk about an Unbragged diffraction efficiency, and Coherence talks about this a lot. And the Unbragged diffraction efficiency is the ratio between the intensity diffracted, yeah, divided by the input intensity. Hello? Is there a question? Okay. So the diffraction efficiency is the diffracted intensity divided by the input. And we're going to derive out these expressions, but it turns out it varies sinusoidally as a function of N1, this refractive index modulation, and D, the actual thickness. So we can see here, if we make the modulation bigger or the thickness bigger, we're going to make this term here start from 0 and increase, and it's going to vary sinusoidally. What we notice that in many, many places, in many papers, people don't talk about, they don't actually calculate this diffraction efficiency. They talk about the Unbragged diffraction selectivity, and they use exactly the same notion. They use this eta, and they talk about the ID, the diffracted intensity, divided by the sum of the diffracted intensity plus the transmission intensity. We also note here, just in passing, that this calculation of the diffraction efficiency, we're not assuming anything about reflections at either of these two boundaries. We're not talking anything about reflections at these two boundaries. And as we'll see, that actually is built into this Coherence description. Okay? So again, this is just some mathematical notation, our description here of our maths and our symbols associated with the hologram. Again, we record our geometries. Okay? And I want to note here something about the representation in phase space. And again, we're going to spend some time at this. So this is in space X, Y, and Z. This here is recording a transmission grating. This is recording a reflection grating. It turns out that if we go from space, X, Y, and Z, into phase space, yeah, and here we're talking about unslanted gratings. So that's what we described up above. So we have here our unslanted reflection and transmission gratings, which we talked about previously, but we have the symmetry between the two. Yeah, so the angle here and here are equal, and the angle here and here are equal. So we have the fringes here perpendicular to the boundary. Here we have them parallel to the boundary. We can come to phase space and we can describe our replay beam here in green, the grating vector here. So these axes here now are going to have units of 1/meters. This is in phase space. And then we have the diffractive beam represented here. And we see that all of these here have got the same, the green and the red, the waves have the same radius, the radius of the circle. And the K here, which is going to be something fixed, it's actually the thing recorded inside the layer, is going to be fixed. So if we change our angle, for example, the K will not change. And this is just showing what happens in the case of the unslanted transmission case. And here's the case of the unslanted reflection. And here's our input. Our K vector now is here. It's perpendicular to the boundaries. And here's going to be our reflective beam. And we're going to talk about this type of representation. It turns out that it's very, very useful. It's very helpful. In terms of our recording here, we've got two waves. and we've got one grating, one cosinusoidal grating, we're going to have to go to a situation where we can have multiple waves, either during the recording or during replay, and we're going to have multiple gratings. We're not just going to have one single cosinusoidal variation, we can have many different modulation components. So this is a beginning of this description, the spatial frequency response, recording cosines, cosinusoidal gratings, finding out what happens with the cosinusoidal gratings, and then going to more and more complicated cases. Okay, so we're going to be talking a lot more about these things, but again, I want to just introduce this so it's not such a big shock going forward. Now, the next page here is handwritten, and I hope you can read my handwriting. And what I've got here is a note, general notation. Okay, so the notation that's going to appear through here, and again, I think this is pretty standard for most places in the literature. We've got the lambda, which often refers to a free space wavelength, the wavelength in free space. We've got this beta, this propagation constant in a medium with a constant relative permittivity refractive index. We've got some average index, a bulk average index of material. So we may have a modulation of that index, but it has to have some average index. And we may be talking about a material, a holographic material, which is index matched to the medium on both sides of it, or there's an index mismatch. Typically, we're going to be talking about materials, though, that have refractive indices which are close to that of glass. So we're talking about average indices of the material of about 1.4, 1.5, something like this. And then surrounded on both sides by, for example, air, though the layer or the holographic layer may be on a substrate material like glass. We have some refractive index, which is a function of position. So we have a relative permittivity, which is a function. And this is equal to the square root of this. Now, typically, we're going to assume that the modulation of the relative permittivity is very, very weak. Okay? And if it's very, very weak, we can use our binomial expression. Yeah, we can take the square root of that, and therefore it's going to be, we take this outside, and the square root of 1 plus epsilon is equal to 1 plus a half epsilon, if the epsilon is very small. And so we describe our index modulation as relatively weak, and therefore we can describe it as being related to the relative permittivity, the modulation of the relative permittivity as shown. Now, in holographic materials today, people are talking about going up to modulations of the order of 0.1, 0.2, which is very, very high. In glass, for example, if you expose glass with an infrared interference pattern to make, for example, a fiber Bragg grating, you're talking about modulations which can be 10 to the minus 2, 10 to the minus 3. In the case of what we call now older polymer materials, you would have been talking about modulations of 10 to the minus 1, 10 to the minus 2, excuse me, 0.01. But nowadays, as I said, there's modulations, materials are capable of recording modulations of 0.1, 0.2. Okay, so again, this might be worth investigating or going back to the original source and working with permittivity. So we have an average relative permittivity, we have the relative permittivity modulation, we have our grating vector. Again, the magnitude is 2 pi divided by the period for the cosinusoidal case. And if we have a spectrum of gratings, we'll have a fundamental component, and then we'll have a spectrum. Yeah, we'll write out our grating as a made up of 2K, 3K, 4K, etc. And we have a grating period. We have a slant angle of the fringes inside. We have a thickness. We're going to have a thing called the coupling constant, which tells you how strongly we get coupling between the input beam and the diffracted beam. And again, this can be written down in terms of the materials as pi times n1 over lambda for a lossless grating. We have a propagation constant associated with the diffracted beam inside the grating. So one of the things we're going to look at is how you can describe the E field inside the volume grating. And as we talk about plane waves outside, we often use plane waves inside, even though the plane waves inside the volume grating are not the actual modes or the eigenfunctions describing the E field inside that space. We have propagation constant of the incident transmitted beam. We have input angles, and we can have input angle inside the grating, inside a material with the same average index of the grating, but we can also have the input angle, if you'd like, outside, in the air outside the material. So we have to carefully differentiate between all these different things. The other thing, again, is notation, is descriptions. So we have volume gratings, and volume gratings are associated with multiple scatter, okay, and selectivity. And there's a whole range of gratings which are volume gratings. So we're specifically talking about recording patterns inside volume layers of photosensitive material. But volume gratings appear in lots of different places. You can have thick surface relief gratings, okay? People talk about computer-generated holograms, which are not necessarily actually thick gratings. They may be thin gratings. So we have to be very careful about our terminology, because these words thick and thin do not actually refer to the thickness or the thinness of the layer. They refer to the amount that's scattered by the grating. This causes people a lot of suffering. You can have holographic gratings. You can have waveguide cases. I mentioned fiber Bragg gratings, where you've got a sinusoidal variation or cosinusoidal variation of a refractive index modulation along an optical fiber. And that can be a dielectric mirror, it can be a volume grating, a wavelength selective mirror. In acoustical optics, you send a sound wave down a crystal, and the sound wave causes rarefaction of the actual material. It actually leads to a densification at different points along the material. And so if you've got a thick crystal and you send a sound wave down there and you put light into that sound wave, it will interact with the traveling sound wave and you will get diffraction. And if you've got a strong enough sound wave or a thick enough crystal, you will get volume diffraction. Now, initially, people who worked on acoustic optics, and particularly here I'm thinking about Raman and Nath, Raman and Nath were using relatively large periods in their sound waves, okay? So they would have had long wavelength sound waves. These acoustic optic cells, they still find application. People have done lots of different things with these things. You've got traveling sound waves, and you can have multiple scatters traveling. Dynamical X-rays, so X-rays inside thick objects. The X-rays have got very, very short wavelength, but still you can have very thick, finely spaced crystals, and you can get multiple scatter, electron and neutron diffraction, solid state, etc. So really, when we say thick and thin, often what we mean is that in thick gratings, we have multiple scatter. People say dynamical scatter. And in thin gratings, we have single scatter. We talked above, when we talked about our model for the hologram, we talked about a transmittance function. And I said that transmittance function could be thought of as the output field divided by the input field. In that case, when the light passes through such an object, we're simply assuming that we have a single variation, a single scatter from that object. And of course, in multiple scatter, it's much more complicated, because the light that's scattered can re-interfere with the other light. And so you get diffraction effects. We've talked about the geometry for planar 1- and 2-dimensional gratings. We can have transmission and we can have reflection, but we can also have intermediate. We can have mixtures of the two at the same time. We can also have finite gratings. So if we imagine a very, very thick volume, and we've got these two finite plane waves are going to cross across one another, we get what as part of space, which is trapezoidal, and you get where the two beams pass across one another, and you're going to get an interference pattern where they cross one another, but not outside that region. And so you can get finite gratings. All gratings, of course, are finite, but in this case, we're talking about finite within a volume. And then the issue of what is actually modulated. So we put in our interference pattern, where we can cause a modulation of the absorption in the material. We can cause and so, for example, in the old case of photographic emulsions, typically what we had was we had silver nuclei formed, and then we had precipitation of more silver around that. And so what we ended up was a negative, something where we had black where there was silver precipitated, and white or transparent where there was no silver. And so that gave us an absorption grating. And on the other hand, we could then process that to remove the silver and replace it by something which was denser, like a halide. In any case, or something which was transparent, like silver halide. So anyways, we can get a modulation of the absorption in the volume, or we can have absorption and modulation of the actual phase, the relative permittivity. And we can have mixtures of these two. And in fact, we can have two gratings formed, an absorption and a phase grating, but they don't necessarily have to be in phase. So where, for example, the absorption grating is a maximum high absorption, we could have the phase grating having a low refractive index. From the above four, we state that we will be primarily examining phase, transmission geometry, well, we're actually going to talk about reflection as well, gratings, thick volume planar gratings. That's going to be our primary concern here. We're going to talk about things like on-Bragg and off-Bragg replay. so varying the replay wavelength and the angular replay. We're going to talk about the evol circle. I might even go as far as talking about evol spheres, because they're a very handy tool for an engineer to get an idea of what's going on. And I'm going to use this because, as I said, it just happens to be very handy, very useful. And it's very much like talking about a signal in the time domain and then talking about its spatial frequency components. It can be very, very useful when you come to some things. In the following discussion, it will be assumed that a perfect single sinusoidal grating is linearly recorded. So certainly in this first lecture, that's what we're going to stick to, cosinusoidal gratings, and then we're going to build up to more complicated cases. It's linear recorded and replayed using TE, polarized light. So again, I'm going to talk about that later. And then we're going to go on and talk a little bit more about different polarizations. Okay? And hopefully we're going to build this up nice and slowly as we go forward. Now again, I want to talk about our plane wave. You're going to get sick of plane waves, but I want to make sure everybody knows what's going on. Here's our plane wave. We've got a unit amplitude, minus jk.r. In this case, it's propagating in x and in y. So this is what we can expand it out, get rid of the vectors. And we can take the kx and the ky, and we can write it here as a beta. And again, that's 2 pi over the wavelength, times the cosine with respect to x, the sine with respect to y. And again, we can expand out our beta. And now we can write it here in terms of the spatial frequency components. And again, the fx here has got dimensions of 1 over meters. So of course, there's no dimensions inside here in the argument. And the magnitude of k is beta is 2 pi over the wavelength. So here's our representation in space, and here's a representation indicating these spatial frequencies, which are shown here on this diagram. So when we talk about a plane wave traveling in free space, we mean something that looks like this. Sometimes we'll have a z here instead of an x, so we'll have a plane, an input plane, which is x and y, and then we have propagation in the z direction. But essentially, this is our basic set of mathematics, and this is important, okay? Because the next thing we talk about is our maths associated with the interference of two plane waves. So now we've got two of these things. We've got an E1 and an E2, and we've got an A1 and an A2, and a K1 and a K2. And the intensity when these two things overlap is we're going to add these two fields together, and then we're going to take the magnitude squared. So we're going to multiply the total field, which is made up of two beams, by its complex conjugate. And if we do that, we end up with the following expression. Here's our two amplitudes. And what we get here is we get the difference between these two. And again, please go away and just make sure you're comfortable with that, because as I said, this is really the basic stuff. And if we know this and we know the notation, we're going to be doing fine. We are assuming both of these are mutually coherent. So we're going to get good contrast here. We've got a wavelength here, these wavelengths. So we have the dark lines are maxima, the dashed lines are minima. And we get an interference fringes, which are these red lines here. And the separation of these two things are given by this, which is equal to the period. So if, for example, we would place a holographic plate in here, right in the middle here, okay, so we're not trying to make, if we had a big volume, we would record something which would look like this trapezoidal type pattern here. But we assume we have a thin layer, so these red lines cut straight through that thin layer of this photosensitive material. And if the two beams are symmetric, then basically we've got an incident angle of this one of theta here and minus theta here if you want. And so we have the theta in here. So we have lambda divided by 2 sine theta. And of course, immediately what we see here is that if that theta is 30 degrees, if it's 30 degrees, sine of 30 degrees is going to be a half. And so we have a period which is equal to the wavelength. Okay? So this would be a typical type of arrangement. And this would lead to a grating which would have the following period, because that's our interference pattern. Now, one thing I want to note here, and again, this is physical, is that if I have these two plane waves, and there's a black one here and there's a yellow one here, and again, I've got particular rays shown, but the phase front here would be perpendicular to this one and perpendicular to this one. We produce an interference pattern, a cosinusoidal interference pattern here. If I do an optical Fourier transform, and I'm going to assume that you're not too shocked by this, but in the lowest level, we could just simply imagine that we place a lens in these plane waves. What we're going to see is that these plane waves are going to be brought to 2 points. All the power in that plane wave and is going to be brought to that point, and all the power in this plane wave will be brought to this point. And so what we have is we have the two corresponding representations here that I'm going to talk about. We have a spatial variation, this cosinusoidal interference of these two plane waves. And I've got this spatial frequency representation where effectively, if this is infinite, These plane waves are infinite, and this sinusoidal variation is infinite, and then this lens would be infinite. We'd have all of the power from the waves brought to points here, and we'd use, for example, maybe a Dirac delta function to express that single point, all the power at that single point brought to that point in spatial frequency. And if these angles are equal, these points are going to be equally distributed here at the different spatial frequencies, these k values. So we have an input domain here in space, and an output domain here in spatial frequency, and we've got this representation of the fields which are equal. Yeah, they're equally valid, they're equally representative. And again, I'm just throwing this in here because I want to make sure people have got these basic sort of ideas in their head. Okay, now another one which tends to throw people is, what is diffraction? Okay, people don't like diffraction. They tend to get a bit scared by diffraction. And it's understandable because certainly it's quite scary. It scares me all the time. So what is diffraction? Or what is not diffraction? Or what else is there besides diffraction? Okay, now most of you are quite happy with the idea of refraction, that light slows down or bends in a denser medium. So we get this change of angle when we go from a low index to a high index, or from a high index to a low index. Most of you are also quite happy with reflection because you like to look at yourselves in the mirror. Okay, so you're all happy with reflection. And this idea that we've got an incident beam and we've got a reflected beam, a specularly reflected beam, and light scattered in the backward direction. And most of you are reasonably happy with the idea of interference. So again, we've got two beams out of phase and they're going to interfere with one another. And I've got them illustrated here. Here we'll be going from a low index material into a high index material. So we get this refraction, this slowing down in this direction. Here we've got a boundary, a dielectric boundary. We have a transmitted beam and we've got refraction, but we also have a reflected beam. And if this is a metal, we're going to have a lot of the light reflected. And here is interference. So I've got the example here where we've got two beams, they're mutually coherent, they're exactly out of phase, and they cancel one another. So we're all reasonably happy with those. And then the question is, what's diffraction? And the answer is, diffraction is everything else, okay? It's pretty much everything else. And in fact, it's truer to say that diffraction is all of these combined together, happening at the same time. And you can go and read about Young and Fresnel and Kirchhoff. Diffraction arises due to the interference of secondary waves. So you have light propagating, you've got some scatter, bending, phase accumulation by that light, which leads to the generation of other waves. And if we think of plane waves, we think about the generation of other plane waves due to interaction with something. Because if a plane wave is traveling in free space, nothing will change the power in that plane wave. It will accumulate phase because it's a mode, but it will not change the amount of power. But when the light interacts with something, you get scatter, and that scatter will be coherent with the light that's being scattered, and so you get interference. Okay, so you get bending and interference and phase shifts, and that's what diffraction is. Okay. So the ideas here are very straightforward, are very simple, but they're very deep. They have massive consequences. So when we talk about diffraction, often what we think about is we think about gratings. And I also here want to emphasize representations of fields. Now, diffraction grating, most of you will have met diffraction gratings, you'll have seen them in operation, you'll have seen rainbows coming out from these periodic structures. What's important is the Fraunhofer equation, or the grating equation here. If I have a plane wave incident on a periodic surface, and this is simply a set of dots, and this is our incident angle, then what we get is we get a spectrum of diffraction orders. Yeah, we have a zeroth order, which is transmitted, and we got a spectrum of orders, and it's essentially I'm kind of assuming that the average refractive index is the same everywhere. So we have a beam coming in here and a beam like this, and again, we're assuming infinite plane waves, so we're not worried about any sort of displacement. And we get a set of diffraction orders, and these diffraction orders, the directions obey this formula here, where the mth diffraction order over here is going to be equal to the sine of the incident plus an integer times the wavelength, yeah, in that medium divided by the period in the x direction. And here we only have a period in the x direction. So it depends fundamentally on the periodicity along the boundaries. And this is true for volume gratings as well. And so we can draw something like this, and we can do a piece of maths, which I do on the next slide, just to show where this grating equation comes from. We note that, of course, the sine of an angle has to be less than 1. It has to be less than 1 or it becomes complex angles. And so we have to be careful that we don't let this become too big. Yeah. So we're going to be expecting that lambda divided by the period is less than 1. Yeah. And if this is a finite number, this m is an integer for the discrete diffraction orders, what we will see is that if that period is big, if we have a big period variation, then we're going to have a lot of possible values of m, which will give me real angles. And so a big period gives me many diffraction orders. We also notice that if we change the wavelength here, we're going to change the angles of the diffraction orders, not of the zeroth. When m is equal to 0, we always have this being the transmitted direction. But if we change the wavelength, we're going to cause these diffraction orders angles to get bigger or smaller. So we have dispersion effects. If we put in white light, the first order for the different wavelengths will come out at different angles, and so we see a rainbow. Another thing just to notice in terms of real gratings is that if I shine, for example, a laser pointer onto a real grating, and I have a wall some meters away, what I'll see out that wall is a set of spots. So we'll have the input spot from the laser, and we assume that the width of that spot covers many, many periods of the grating. But we're going to see a set of dots, diffraction orders. They're going to separate out, and we'll actually see them, because they're finite, as dots on the wall. I'm going to talk a little bit about that later. So this gives me the grating equation. This gives me an illustration of the diffraction orders. There's two other ways I can represent what's happening, what's coming out. I can assume that I have a zero transmission with a particular set of phases, spatial frequencies, okay? And I'm going to have then a power spectrum. I can go and plot the amount of power which is coming from this one and put it here. So this will be a power. And then the plus and minus, if it's symmetric, they'll have equal power. And we'll have plus and minus 2. So this here is power as a function of the spatial frequency, as a function of the angles. And you can see here actually that I said to you that if I put light through this grating, I'm going to see a set of spots on the wall. It turns out that the set of spots I see on the wall, yeah, if I replay in the plane of the grating, are going to look like being associated with these points with all the power in these various orders. So if we put light through a grating and we look at what that light pattern far away, it looks a little bit like this representation where this kx and ky are actually distance on the wall. I notice here also that I've got a separation between these two in k space, and I associate that with kx, with the actual grating vector magnitude in the x direction. So we've got our period here, and 2 pi divided by that period is going to give me my magnitude of my grating vector. And if I look at these little points here that have all this power, which are associated with these diffraction orders, I'll find out that in phase space, they're separated by a distance which corresponds to this kx. Now, of course, in the real world, if I move further and further away from the wall, I'll see the distance between the spots on the wall gets bigger and bigger, okay? But that's a function of the actual propagation through free space. Sorry, did somebody say something?
Yes, sorry. We have a question
yes,
on
please.
the chat. Could you please look at the chat?
Oh, sorry, excuse me, the chat. Okay, sorry, no, I'm not so used to that. 1 second. Let me see chat. So sorry. Sorry, I cannot actually see the chat here. Excuse me.
Okay, I'll just read the question.
Can you read it? I'm very sorry. I just don't see it here right now. Go on. Sorry.
Would you please be so kind to explain once more the difference between thick and thin gratings from the scatterer's point of view?
Okay, so I will talk about that in much more detail later. Okay, I promise. Yeah.
Okay. And there are like 2 more questions, but regarding these. So.
Okay. Yeah, I promise I will talk about thick and thin in much more detail. Right now, I just want the idea that the thick and thin has nothing to actually do with the thickness of the layer. And the thick is generally associated with multiple scatter. So the light comes in, it interacts with the object, and then the light that's scattered is scattered again. Okay, so there are multiple scatters, whereas in thin gratings, the light essentially passes through the material and there's only one single scatter. But I will talk about this in much more detail. Okay, and I will give examples. Okay, is that okay?
Yes, thank you.
Yeah, I promise I'll do mathematics. I'll show you exactly, okay? Okay, so here's a little derivation for that grating equation. Outside all gratings, the grating equation, and it's outside, defines the angles at which all the diffraction orders travel. Here's again our periodic structure. I've got the same notation, and you see this point A, B, C, and D on these rays. And I've joined A and C, and I've joined B and D. In air vacuum, for constructive interference, the lengths have to be equal. So in other words, I have to make sure that the path traveled between A and B and C and D is an integer times the wavelength, or else I get destructive interference. And there's a very interesting description of Feynman of this type of effect and how you can actually explain the operation of a grating using this interference type effect. I is an integer and lambda is the wavelength. And we can go away based on the grating, and we can show that the distance AB minus CD is equal to the period in X sine of theta I minus sine of theta 0. That's famously trigonometry. And constructive interference only occurs when we satisfy the grating equation, the Fraunhofer equation. And this has been very rigorously and accurately tested, and it's been shown that, for example, it's related to, or it's a consequence of, conservation of momentum. From this equation, we can see that theta I is a function of the wavelength, so all gratings are dispersive. Put in white light, you get a spectrum, a rainbow. We can also see that the larger the period, the greater the number of diffraction orders, and that the period X must be greater than lambda to get any orders. If I make this period smaller and smaller and smaller, eventually we're going to get two beams, a diffracted beam which is traveling parallel to this boundary, and then we make the period even smaller, we're not going to see that anymore. And this is very much like the functioning of ordinary materials, where we have very fine-grained structure, which is smaller, for example, than the wavelength, and the wavelength averages over. So we don't see the diffraction effects because the beams that are scattered are evanescent beams, effectively. The grating equation, this is important, tells us nothing about the amount of power in the diffraction orders. It tells us nothing about it. It only tells us their spatial frequencies. It also doesn't tell us, for example, if one is going to have more power than another. It doesn't give any preferential information whatsoever. It doesn't indicate anything to do with selectivity. The Bragg condition, however, tells us something about selectivity. It still does not tell us anything about the power in the diffraction orders, but if you want, it tells us about a possibility. And the Bragg condition and the existence of an on-Bragg and off-Bragg replay are fundamentally involved in this idea of thick gratings. So we're getting there, okay? And here we have this diagram. We have an input angle, we've got an output angle. And what's critical here is the idea that this is a ray coming in. These two are the wavefront. And this ray comes in and it interacts with this particular fringe, okay? Now, of course, we can't just treat these things discretely. This is not like a Venetian blind. This is a continuous cosinusoidal variation of the refractive index, for example. But we can take this ray here and say, well, we're going to get some light scattered from this. We could imagine this being slightly higher index than surrounding it. So we get some light scattered in this direction. And then we have this part of the same wavefront comes in and is scattered by some point along the exact same fringe, but further inside the volume. And we're looking for conditions where these two rays, when they have propagated down here, they're in phase. If they're in phase, we're getting constructive interference, yeah? And so we have some particular significance to this direction because the reflection of the rays from the two different parts are in sync. So again, we have a thickness, we have a period here, this would be the period, sorry, that should be the period. And we have a representation on the evil diagram. Here's our input beam. Here's our fixed K vector. Again, the grating vector, that's fixed. We can change this here, we can rotate it, but if we keep the wavelength constant, we're always going to be inside this circle. And then we reproduce this particular diffraction order. Again, this is in phase space. The circle has a radius, a beta 2 pi over the free space wavelength times the refractive index. And it turns out that we can show that for this Bragg condition to be satisfied, it must obey this following relationship. And again, we have an integer here. We've got the replay angle, we've got the slant angle here, the period, and this now is the period here, it's the slanted period, it's inside the volume, and we have an integer. So we can in fact have, for a single grating, we can have multiple on-Bragg replay conditions. If we change our angle yeah, and we change it enough, we may come back on Bragg. If we change our wavelength and our angle, we may be on Bragg. So a grating can have multiple Bragg conditions. And again, this is not telling us anything about the amount of radiation in that particular direction, but it is telling you that it has some special significance because we get this in-phase reconstruction. So we can go away again, just as we did in the grating case, and we can derive this out. The Bragg effect is usually represented diagrammatically as follows. Okay, and again, Bragg, this whole thing would have been derived based on X-ray diffraction by crystals. And of course, the X-ray wavelength is very, very small compared to the size of the actual crystals. And so we get diffraction of the X-rays by the crystals. And if we've got a crystal which has got big periods, then basically we're going to get something which is like almost like single scatter. But if we replay at particular wavelengths and at particular angles, we're going to have a very strong Bragg effect. And again, we've got our A, B, C, D, and we've got that for constructive, we're going to have this relationship so that these are exactly, and these two rays are exactly in phase over here. And we come along, we have input and output. Therefore, we can go back and do something very much like we had with the grating equation. And in this case, however, we don't have the single array of points. We have points spread out in two-dimensional space. And so we get the Bragg law, or the Bragg condition, because we've got reflection at two different planes. This condition is stricter than the grating condition. It's stricter, yeah. For any input, the grating equation predicts diffraction orders traveling over a full spectrum of output angles. The Bragg condition only predicts a particular order will exist for a particular input angle. So the Bragg gives you a subset, a particular subset of the waves associated with the grating equation. Effectively, diffraction is distributed in one dimension for the grating equation, but in two dimensions for the Bragg law. This can perhaps be better illustrated using a volume hologram. So for this case shown, the grating equation predicts the following sets of orders. Okay, we can plug this in here. Here's our grating. We've got a slanted grating. We've got our input plane wave. We've got this fringe. We've got the two waves scattered off at different points of the fringe. And all our angles, our input angle, our output angle, our period here, our period along the boundary. And we've assumed this is uniform. So this is the exact same period you'll have over here. Okay. So again, we have a spatial frequency. The grating vector here is going to have a spatial frequency in X and a spatial frequency here in Z. And we assume reflection along fringes of constant index. And due scatter from the same fringe, these must be equal for constructive interference. So this has to be equal to this, or this has to be equal to this. And we get the following, that this has to be equal to this. When phi is 0, in the unslanted case, this is our Bragg condition. Okay? So we have the following Bragg condition. So again, just to get you sort of familiar with this type of idea, and we have the Bragg grating equation is true for all gratings, whether they're considered multiple scatter, thick or thin. In the Bragg condition is usually associated only with the thick gratings, where we have multiple scatter. And we can come along here and illustrate this. Here we have our two beams interfering. We have our thin holographic material layer here, and we record our grating. And we can take that grating, so the grating now is fixed. We've got the same K everywhere. And here we replay on Bragg. So we replay with one of these beams here. And we have our red beam reproducing our blue beam due to reflections at the boundaries. And so we see when these things are cross one another, we see that their maximum is crossed with a maximum here at every point. Okay. Here we've got on Bragg, but we've changed both the angle and the wavelength. So we have a different separation between these lines coming in. We have an input and diffract, and we see the angles are changed. So we can change our angle, we can change our wavelength and still be on Bragg, but the angles are different, the wavelengths are different. And finally, we can have, again, this can be thought of as a multiple scatter type arrangement, okay? And in this case, what happens is we've got a much bigger angle, we've got the same wavelength, we're replaying with the same wavelength, but we've changed to a big angle, and we actually see an effect which is equivalent to having a grating with a fundamental component, which is 2K. So in effect, the way here we're getting light from here to here is we're getting scattered by the grating to produce this. In this case, actually, we've got multiple scatter within the object. We've got to get a scatter and then another scatter. And the total result is as though we had a grating in there with a period, which is actually half the period of the grating. So this idea of harmonics. In all of these cases, we can obey the grating equation, the Bragg equation, and so we can have a preferential difference of scatter. And I talk about this a little bit more detail. I sort of draw it out more carefully, indicating some points where they overlap in the following down here. It's a little bit more colorful, I think, and it's going to be maybe a little bit more clear if you like it or not. Now, I make it 9:45, and I sort of intended to sort of stop here. I left a blank sheet, okay? As I said to you, I'm going to come down here later. We talked about thick and thin. I'm going to talk about complex transmittance, and I'm going to talk about thin gratings. That's what I'm going to talk about next. Amplitude and phase, and how thin gratings work. And then we're going to move on, and we're going to talk about thick gratings. So don't worry about that. We'll be talking about thick and thin gratings later, okay? And we're going to be lots of mathematical examples down here. But I can stop there now and give time for some questions, if there are any questions. So we're a quarter to the hour, okay? So are there any questions? No questions?
Yes, we have one more question.
Very good.
In the chat. I would like to ask about what are the factors or conditions that determine the thickness of the gratings?
Okay, so down here, I'm going to derive out a set of equations, okay? I'm not sure where I have this. I'm going to derive out a set of equations which will differentiate, yeah? So we'll have thin gratings are Raman-Nath type gratings, and thick gratings are Bragg gratings. And this is the classical way this curve was presented. Nowadays, what you often see is people plotting the log of this expression and the log of this expression, in which case you get two lines in this logarithmic space. And we'll have the actual parameters that you use. They're defined here, yeah, this Q prime parameter, which is the magnitude of the grating vector squared times the thickness, divided by the phase constant times n. That's one parameter. And the other is this new parameter, which is the coupling constant, which we defined, times the thickness. And if you find that the Q prime times the nu is less than 1, you're below this curve here. And that means you have a Raman-Nath type grating. So that's typically associated with a large period or a low refractive index modulation. And over here, if your Q prime divided by nu is greater than 20, so you're under this particular curve, then basically you have a strong Bragg grating. And the difference between the two is shown here in terms of diffraction efficiency. So here you see the type of variation, I mentioned this before, this sinusoidal variation, where you can get up to 100% diffraction efficiency for thick grating. Whereas with thin gratings, you typically have some sort of diffraction efficiency which is related to the square of Bessel functions, where one here, this is for the first diffraction order, the second one will be 2. Okay? And then there's a huge region in here which is called an intermediate region. Okay? Now again, in the intermediate region, you really require more accurate types of models. The Raman-Nath model is often talked about an in-wave model, but it has no selectivity. There's no Bragg effect associated with it. The Bragg then, basically, mostly we're going to talk about the two-wave type model from Coherence, so we get a good feeling for what's going on. And so there's nice, relatively nice, simple analytic expressions. If you want to cover the entire space, you've got to start talking about rigorous electromagnetic models. Okay, and again, this type of curve is explained and discussed in the references I gave you. And there's, of course, a different type of selectivity associated with these materials as well. So again, I'm going to talk about that in more detail as we go forward. Okay? Is that all right?
Yes.
Is that okay? Okay. So as I said, we'll get to that now, the next lecture. Yeah, and then we'll go on from there. But it's very, very important you understand our background here. Any other questions?
If you have questions, you can again type them to the chat and we will read them for Professor Sheridan.
Okay. Now, I would actually say the following though. This is an opportunity for you to speak English. Okay? And it's like cycling a bicycle, I'm afraid. You can read a lot of books about cycling a bicycle. Okay? But that doesn't mean you can actually cycle a bicycle. So it's a really good idea to talk. And once you start, it's hard to stop.
By the way, I wanted to ask, could you send us this file?
I will. I will. Yeah. Now, the one problem or one issue with this file is, as far as I understand it, this first file is about 100 megabytes. Might be 130 megabytes. Okay. So there might be an issue with the size. I might have to break it down into smaller pieces or something. Okay. The other possibility is if there's a Google Drive or something that I could put it on a Google Drive. Are all of you familiar with this idea? Now, I'm happy to do it for the university. I really don't mind how we do this. Yeah. Again, I promise you, the book from Sims is very, very good, and it's free. Yeah. So in some ways, what I'm trying to do here is I'm trying to talk through this very slowly and carefully, and then you can look at the Sims book and you'll get a lot more information in the Sims book. I promise. Okay. The Kogelnik paper can be quite difficult. Okay. It can be quite a bit of work. Yeah. But again, hopefully that's the source material for the first part. If you look at the different sources, you should be able to figure out what I'm saying. But I'm very happy to supply these slides to you. But as I said to you, compared to the Sims book or Kogelnik's paper or the paper from Gaylord, it's very, it helps me to talk, but it's not necessarily filling in every step. Yeah? Do you understand?
Yes, we do.
Okay, that's good. So I'll try and sort something out to get you access to this, and it may be a Google Drive. Are there any other questions?
I have a question, Professor.
Sure.
How far actually the analogy between scattering and diffraction goes?
Well, you see, typically, it's really about terminology, okay? Now, scattering is probably a broader term than diffraction, in the sense that people talk about incoherent scattering, okay? And people talk about particles being scattered. When we talk about diffraction, we're talking about something which is directly related to the wave nature, okay? So if you want, you can think of scattering, yeah, as being like reflection, okay? But diffraction involves more than that. It also involves the interference, okay? Now, people talk about light scattering, and often when they talk about light scattering, they're talking about single scatter, yeah, what's called kinetic scatter. And so they're talking about a single interaction between the light beam and an object, okay? So a single diversion of the light, if you want. Diffraction is more complicated than that because it covers a greater number of cases. Yeah, it's a general case. So you can get diffraction from the edge of an aperture. And very often you can treat that as single scatter. And you can also get diffraction from volume holograms, where you have multiple scatter. In terms of the fringes, I drew there two rays, an example with two rays. So in order to explain the Bragg effect, I talked about this case here, where we could imagine that each one of those points is like a point source, okay? So each one of these points is, so the light comes in and generates a spherical wave coming outwards from that point source. And then when we add together all these point sources, which are equally separated, we're going to end up producing a set of plane waves. So only the plane waves correspond to directions in which we have constructive interference. And so we could think of this as a single scatter type of grating. Whereas with the Bragg effect, we have this notion of multiple scatter, yeah? So in effect, we could think of this line here, this fringe, as having a set of point sources all the way along that fringe, yeah? And only in particular directions are we going to get this constructive interference.
Yeah, that's a great answer. Thank you very much. But are there any articles or sources that regard this process from this point of view? From like, because this is regarding diffraction essentially as a scattering. This would be cool to read somewhere about.
Yeah. Well, I to be honest with you, I think I may understand what you're saying. So there are numerical methods. There are many numerical methods to calculate diffraction, okay? And one of the methods involves locating sets of point sources effectively. So they talk about sampling, or they talk about replacing a surface, for example, by a set of appropriately located point sources. Yeah. And then they go away and they may vary the amplitude of the point sources, or they may vary the phase accumulated at the point sources. But to be honest with you, I can't think of there's some excellent books out there. There's a book by a man called Stamnes, Stamnes. I can't remember the title now, but he talks about a huge range of wave phenomena. So for example, he talks about producing a Fresnel zone lens in water by driving pillars into the sea. And this was actually used to implement a electrical generation. So they focused the waves coming from the sea into a particular cove, and they used that to drive an electricity generation system, okay, by focusing the power of the waves. So he talks about a wide range of wave phenomenon and diffraction phenomenon. I'm not quite sure if I fully understand what you're saying, though, in terms of, because, you know, I mean, in the sense that I think Fresnel and a lot of the guys would have thought about diffraction in this way as series. So the wave comes in, interacts with some intermediate object, which produces a set of distributed spherical waves with different amplitudes and different relative phases, and then that produces the diffraction pattern. So, but a specific paper, you probably, I guess you have to go back certainly at least to the 50s or 60s, where people would have talked about things like this. There's a very interesting area called geometric diffraction, where people talk about this mixture of rays and sort of point sources to produce diffractive effects, which I quite enjoy that type of description. As you probably picked up, you see, I'm an engineer, so I like to have very, very concrete ideas in my mind as far as possible. But we could talk about this offline if you're interested. I mean, if you put a few words together and send it to me, I'd be very happy to talk about this with you, because this fascinates me.
Yeah. Thank you very much. Yeah, I will do this. Thank you for your.
Thank you. Any other questions? So thank you all for coming. And I think it's not tomorrow morning. I think we're on the Thursday morning. I have to check the schedule. We go back up here to the schedule, and let's just see, sorry, just to check. So the 26th, and the same time, same place, ladies and gentlemen. Again, please make sure if you're registered, yeah, you're coming, because there's going to be some sort of exam at the end of this for you guys. And we might force some of the professors attending or their students to do the exam as well. We'll see what happens, okay? So thank you all very, very much for attending. Perhaps perhaps everybody could leave and I could just have a little chat with the people from ITMO, if that's okay. Is that okay?
Yeah, of course.
Okay, thank you very much.
Thank you. Thank you all for coming.
Thank you.
I hope it was useful. If there's some things you don't like, let me know and I'll try and make things better. So now we have the students from ITMO and the staff from ITMO, is that correct? Hello?
Yes, at least some of us are here. Yes.
Very good. So again, specifically for you guys, I tried, again, I don't know what people know, okay? And I don't know your system. So I wanted to try to start off slow and steady and careful. I don't want to end up talking about things that people don't understand. And also I want to talk about things which I hope will help with labs.
Pardon, what about labs?
So I hope the descriptions I'm giving are applicable to some of the things you're thinking about doing in relation to the labs.
Yes, that's true. We don't know how well all the students are prepared either, because many of them have entered our master's programs without, they came with different backgrounds.
Okay.
That's really great that you explain all these basic things about holography.
Okay.
We could have missed them in the previous iterations, so to speak.
Okay. I said, I have many very interesting, exciting things I can talk about, but if we don't have the same language, it's not really much use, you know. And I don't want to drive students crazy. So at least they should have some context for what I'm talking about. In terms of, so I have, you know, questions. Am I talking too fast?
In my point of view,
No, it's
you
nice.
talking and yeah, it's nice, I think, but students maybe have like another ideas about it.
Yeah, are the students happy?
Because yeah, I hope so, because I think this is a great introductory lecture, so it's very interesting and like not so in terminology and all these things, very like easy to understand in my point of view.
Okay.
Especially like students from ITMO already have course on holography, like in
Okay.
the bachelor's, so maybe for them it was like the repeating of what they know, but maybe new
Okay.
students don't have holography in their previous university, so for them it was very useful, I think.
Yeah. Also you understand, I'm worried about terminology, that I use different symbols, and also I'm worried because I speak in English. So I mean, you know, I took courses on electromagnetism and optics in Ireland before I went to do my master's degree in Georgia Tech. And so it was the same language, or at least I thought it was the same language, and it was the same material, but I found it very difficult because the symbols, the starting point was very different. So for me, it's very interesting to learn how to do this better, okay? So if you have a problem or you don't understand something, if you can tell me, that will be good for me, okay? I will try to make all this material available to people. But if you have a problem, you have to tell me. If you don't tell me, my job is to explain things. So if you don't tell me you have a difficulty, I cannot explain better. Yeah. And I always say to my students, if you don't ask a question, the only bad thing you can do is not to ask a question. If you don't understand something, you have to ask. If you don't ask, then you're neglecting your duty. Yeah. So the students have to ask the question, okay? Or else I don't know. Yeah. I can try and explain better, but if you don't ask, I can't explain better. Okay? I don't know, and I cannot see pictures of you. I don't see video of you, so I don't know if you know. I can look at your face and say, "Oh, he doesn't know," or "She doesn't know." And if you're afraid to ask questions because you will be embarrassed, that's a very silly way to do things. You shouldn't do that. Yeah. So please ask, and if you want, you can send me email in private if you're ashamed. Okay. And we will see how far we will get. Okay, ladies and gentlemen. Yeah. So please help
There's
me.
another message in the chat. So Mikhail said that you are a very great lecturer and everything was completely clear and understandable.
Okay. Well, when everybody has passed the exam, I'm a great lecturer. Okay. Until everybody has passed the exam, we don't know yet. Okay. Okay.
Okay. Okay. Yeah.
Okay. So just for the staff, I don't know if the students want to leave now for a minute. If all the students can leave, and then maybe I could talk to the staff. Thank you very much.
So Professor Sheridan, regarding your presentation, so you will send it to the students by yourself, or you
Well,
maybe you
what I will do is, I'm actually very bad with computers. I'm sick. Every 5 years there's a new computer, a new software, and everything. So my wife is much more intelligent than me. So I will ask her or my son to help me set up a Google Drive. I have such a thing. And then what I can do is I can supply access to that Google Drive to anybody who wants. Okay? I think, because the problem is, this file now is, as I said to you, is maybe 130 megabytes. And I don't know if my email will allow me to send a file that's 130 megabytes. And it might take a lot of time and energy to try.
It will try to download it.
Yeah. So
like if you use Gmail, it will like automatically like upload this file to Google Drive by itself.
I think so. I've seen this happen, but I really believe I have infinite capacity to mess these things up. Okay. Really, it's very easy to make stupid mistakes. Okay. So, you know, again, For me, what's important in relation to you guys is that I'm doing what you want. So if I'm spending too much time on something, or I'm going too fast, or you have to tell me. I'm not a very sensitive person with these things. Yeah. I work with people in companies. And so, you know, just tell me to do it different and I will do it different, or I'll try to do it different. Okay. So it's very important because it's your students. I don't want to mess up your students. Okay. I really don't. Okay. So, you know, so I have to force the students to tell me if I do something wrong, but also I have to force you to tell me if I do something wrong. Yeah. Because if you don't tell me, I will not know.
Yeah, okay, it's clear.
Okay, thank you.
Okay. Well, we see going forward. Okay. And let's see what happens. Yeah. So thank you very much again for asking me. I hope it's useful, and I will be here again in not tomorrow, the day after tomorrow. I have given Vladimir my WhatsApp telephone connection, so I can give this to you guys as well, or he can share it with you. And if you have any questions, just let me know.
Okay, thank you very much. Yeah, maybe it will be useful for, you know, rapid connection with you, but I don't think that we have any issues, because today was very good. Everything very good. So.
And just an indication as well. So we started off, I think you said, with something like 80 people. I think I saw at the end there was maybe 40 or something. Do we have an idea? Is somebody going to collect that information of how many people attended? It's useful for me to know, you see, because again, it's a way to find out where people are listening from and who's listening, you know.
Okay, I can do that. I think the maximum today.
I think also your staff would be interested. Because it's good public relations, you know.
Mm-hmm. Yes, that's right.
And if I make such a Google Drive, I'm very happy. I can send you the information, and you can send it to the other people as well. Yeah, it's just, as I said to you, it's
to the attendees. Okay.
Yeah. You know, we can. I mean, it's interesting. It's you have information, you can use it. You know. Also there, you know,
that's right.
you probably know this very well, but I think in my research there are maybe 6 people in the world who know what I do. Okay, and 3 of those people hate my guts. Okay, so basically I always like to keep an eye on what's happening. Also, there's possibly some people I've never heard of. This is very interesting because I keep meeting people who do holography and I don't know them, and that's just amazing. Yeah, I'm always very embarrassed. Very embarrassed, you know, because I've been working for 30 years with holography, and then I meet people and I have not heard of their work. So, okay, gentlemen, thank you very, very much.
Thank you.
Have a good day.
So,
thank you very much.
Yeah, if we have anything, we will email you.
Oh yeah, just mail me. I think I'm quite happy. You know, if you're you see, the point is, if you're happy, I'm happy. It's very simple.
That's great.
Yeah, because I like to talk about this stuff, and my main worry is that I don't explain it clearly enough. Yeah. It's also, there's always a tension between explaining something in a plausible way and explaining it rigorously. Because the problem is, if you explain it rigorously, there's so many little pieces that people won't follow. Yeah. So you have to try and make the food digestible. And, you know, so we will try.
Yeah.
So cheerio. Thank you very much. I look forward to visiting Petersburg
thank you
someday.
very much.
I really, really want to visit St. Petersburg someday, you know, and I want to visit the University of Denisuk. Yeah, very much.
Yeah.
So for me, this is very much an honor. Yeah. Okay. Thank you.
Thank you. Goodbye.
Bye-bye.
Yes. So bye-bye.